Coming up, the award-winning Lotus Flow coating process, why this pipe coating is making a big difference for the oil and gas industry, plus a breakthrough for better air quality. And machine learning, it's a tech buzz phrase, but do you know what it means? Our expert is in-house to explain. That's next on this episode of Technology Today. We live with technology, science, engineering, and the results of innovative research every day. Now, let's understand it better. You're listening to the Technology Today podcast presented by Southwest Research Institute. Hello and welcome to Technology Today. I'm Lisa Pena. Breakthroughs and Ask Us Anything coming up. But first, SwRI Institute scientist Michael Miller is here to discuss Lotus Flow Superhydrophobic coating used in offshore pipes. The technology is one of our two R&D 100 award winners for 2019. Congratulations to your team, and thanks for being here, Michael.
Well, thank you, Lisa.
So, Michael, first question, what is Lotus Flow? How do you describe it?
Well, Lotus Flow is both a coating technology as well as a process to apply the coating, which deposits a coating on the internal surface of pipe structures. And the purpose of this coating is to mitigate deposits from adhering to the internal surface of that pipe. And the deposits that we've targeted are things like waxes, or paraffins, as well as asphaltenes, which are tar-like substances that are very tenacious on just about any kind of surface. And these deposits present a big problem to the oil and gas industry when we're recovering oil from deep offshore wells, in that they tend to plug the pipe in these wells. So the coating prevents the adhesion of these deposits and allows product to flow consistently and continuously.
So what does better flow in the pipes mean for the industry?
It means a lot, because any plugs that develop in a deep offshore well potentially can cost millions of dollars a day to unplug. And it also costs a lot of money to prevent the plugs from occurring again. There's a number of mitigation strategies that are used in the oil and gas industry, which require that they pump millions of gallons of organic fluids, things like methanol, down into the well, to mitigate these substances from adhering to the surface of the pipe. So the coating basically takes the place of these other solvent-based mitigation strategies, which they present a big environmental impact, potential impact on the environment if you have leakage of those solvents.
Take us to the offshore drilling site for a moment, because we think of them as, out there in the middle of the ocean, separate from our lives. But really, what's going on out there does impact our day-to-day lives. Can you kind of connect those dots for us?
Sure, yes. Any additional costs that it takes to recover product, meaning oil product, that will be processed later, let's say, into a fuel like gasoline or diesel, any added cost to that eventually affects the consumer. So anything that can be done to reduce the cost of oil recovery, particularly in these situations where let's say a plug in a downhole pipe would stop production, is a big deal to the industry and to us as well.
Yeah, for all the things we use oil and gas for.
Correct. It's not just fuels. It's also plastics and other products that are derived from petroleum products.
Yeah, good to know, because like I said, I think that's just, we don't really think about how we get the products and the fuel that we use every day, but I mean, it's important for all of us, really.
Yes, it's everything that we touch today is probably a petroleum-derived product. we try to mitigate everything that has a potential impact on the environment surrounding that industry, and this is just one of them.
So let's talk about the name Lotus Flow. I like that story. How did Lotus Flow get its name?
Well, Lotus actually was meant to be a code word for this development project during the R&D phase of it. But lotus comes from really the lotus leaf flower. And if one were to look at the surface of the flower from the lotus plant, you will find that microscopically it has a structure to its surface. It has a surface topology. It also has a very interesting biologically derived coating on that surface. And in effect, what happens is the surface of the lotus leaf is actually superhydrophobic, which allows water droplets to fall very easily into the center of the lotus leaf. So while we're not applying these microscopic structures to our coating, the coating is superhydrophobic.
Let's talk about that term a little bit. Superhydrophobic.
Yes.
How do you define that?
So superhydrophobic is anything that will, for example, cause a water droplet to bead up is the best way to visualize this. Just like if you were to wax your car, which some people apparently still do, the idea is to try to get it as phobic, meaning it dislikes the surface, and the surface in this case would dislike water. So a water droplet would bead up. And we actually make a measurement. It's a good question because we actually make an analytical measurement of that effect, which we call the water contact angle. So the more spherical the drop is on that surface, the more hydrophobic it is. And we have, as scientists, we have defined these ranges of what that water contact angle is and how we classify it, whether it's hydrophobic or superhydrophobic. In our coatings, the contact angle is high enough. In other words, if you were to look at the water droplet, it would be very, very spherical, that we call it superhydrophobic.
Okay, so because of this coating that in essence repels liquids,
correct,
on the inside of the pipes, that allows for better flow because things
yes.
are not just clumping up in there.
Right. Now, it gets quite a bit more complicated.
All right.
Because
I imagine.
In a flowing pipe that's producing an oil recovery process, that you have a very complex matrix of oil product as well as some component of gas in that flow as well. So the interaction between, let's say, the deposits that we're trying to prevent from adhering to that surface are actually in a surrounding matrix of oil as well. So that interaction becomes very complex. But we have just established that we need to be in the superhydrophobic range in order to mitigate the adhesion of the deposits that we specifically targeted.
I've seen photos of the process of making this coating, and there's a lot of, I guess, light, and it
yes.
looks very colorful. Can you describe that process for us?
Yes, the process is really key. We use a plasma. It's a plasma process. It's a vacuum process. We actually make use of the pipe that we're coating as a vacuum chamber. Okay. And we evacuate the pipe, and then we introduce gas, in this case is an argon gas, along with these chemical precursors. And then we stimulate the pipe electrically to ignite a plasma. So some people call plasma the fourth state of matter. A plasma, as we create in this process, is highly excited states of both the gas that we've introduced as well as the chemical precursors. They're highly excited. And excited in the sense that they're their electrons have been pushed to an excited state. And when they return to their ground state, they emit light. So much like your fluorescent bulbs, which work basically on the same principle as forming a plasma, they emit light. This process also emits light, and it's a beautiful cobalt blue light that is emitted in this process. But the idea here, the reason it's important to ignite a plasma is because we're trying to actually excite these molecules, these chemical precursors that I mentioned, to a point to where they actually fragment. They kind of break apart, but they break apart in a very controlled way so that they also form ions. And those ions are then accelerated very rapidly to the inside surface of the pipe. And when they're accelerated very rapidly, they collide with the surface, and then they undergo additional reactions. It's what we call a polymerization reaction, which then forms this conformal coating on the inside of the pipe.
And is all this done in a lab somewhere, prior to installing the pipes where they need to go?
Correct. Yes. So in order to do this process, we have to build a facility that would accommodate long lengths of pipe. Normally, a typical length of downhole pipe is about 40 feet per stick. We call them sticks. So in order to have enough of a production rate, one has to build a facility which can handle a number of coating lines simultaneously. So we built what we call a pilot facility to demonstrate the process to do this. And during that process, we were able to demonstrate that we can coat multiple lines where each line has two sticks, two of these 40-foot sections of pipe, which are coupled together. So 80 feet total per line. And we ignite a very homogeneous plasma along that entire length, which is or was one of the biggest technical challenges because it's actually quite difficult to ignite a plasma over a long distance like we do. So once we determined how to do that and how to do that consistently, then we knew we had a good process to deposit this coating. So now that technology that was put in place as a pilot facility, along with the chemistry that's associated with Lotus, was transitioned to a third party. That third party is Shawcor, and they have now built a full-scale facility to produce large quantities of coated pipe. In our case, we produced about 160,000 feet of coated pipe, and that was done primarily just to validate, or to be able to validate, the performance of the coating in a real case scenario. In other words, that pipe was installed off the coast of Texas, in the Gulf of Mexico, in a deep, very deep well, about 20,000 foot in depth. And that's just to be able to validate. Normally when we do experiments in the laboratory, we may set up something which we look at, let's say, 10 different specimens, and we run some tests, and perhaps we derive some statistics on the results. In this particular case, in order just to validate the performance, we have to coat about 20,000 feet of pipe, install it downhole, and validate the performance. So it's a much, much more difficult target to achieve just for validation.
So it was validated, and now a company is doing this day to day, and so this technology is in use now. It's
fully commercialized now. One can request or order coated pipe with Lotus Flow coating, and purchase whatever quantity you request.
So I know one of the things that you're especially proud of, and as you mentioned earlier, is the environmental benefits.
Right.
So tell us a little bit about how this process is better for the environment.
Well, just not having to use organic solvents to mitigate the adhesion of these deposits deep offshore is, I think, a big step in preventing environmental impact due to, let's say, accidents, leaks, just the handling of organic solvents. These are also volatile solvents. So that combined is, I think, is a pretty big deal.
This is a pretty involved process, and you're talking about plasma, sparks flying, the whole works. How on earth was this process discovered? Is this something you just stumble upon, or does this take many years of trial and error?
Well, the development time is about 10 years. So this was not done overnight by any means. And we have to separate the discovery of both the process and the chemistry. We really started looking at the coating chemistry initially, and that was done at a very fundamental level. We were actually started with doing molecular simulations to try to understand why such deposits stick so much to, let's say, bare pipe, and then we wanted to answer the question, well, can we develop a coating that would at least mitigate that process? And that was done at a very fundamental level. And then we started off trying to demonstrate our hypothesis by coating in a more conventional process chamber, coating coupon-sized specimens, literally 1-inch square coupon specimens, and doing some analytical tests on that. And at some point we said, yeah, I think we're going towards the right direction in developing this. We came up with a coating chemistry that we felt had a very good chance of working for different types of deposits.
We've talked about superhydrophobic really not being a new element for coatings, but what really is different about this particular process is the durability.
That's right.
If you can speak to that.
Yeah, so you can pick up any journal these days having to do with coating technologies or surface science, and you'll find any number of articles on superhydrophobic coatings. That part is really not new. What is difficult to achieve is superhydrophobicity in a very durable coating, and we needed to achieve that because the conditions in the depths of these deep offshore wells are really quite aggressive, and most conventional or known superhydrophobic chemistries and coating processes would just not give the durability that was needed for this application. So that's really a clear and distinct difference between the conventional wisdom, if you will, and this particular coating technology.
And likely one of the reasons it was recognized for the R&D 100 award, which I want to touch on now. We did mention in last month's podcast that the R&D 100 award, it's a huge honor. We had 2 winners for 2019, and the Lotus Flow coating was one of them. Since 1963, R&D Magazine has presented this award annually, and SwRI has won 45 awards over the years. So what did it mean for you and your team to garner this recognition and join this elite group?
Well, it was really terrific. It's really a testament to the team, and I can't emphasize that enough. This was a multidisciplinary team. It's very much like a puzzle. Every element of that puzzle has a unique shape, which equates to people's unique skills. And every person involved in this team played a very critical role in developing this technology and transitioning it to full commercialization. So it's an award for everyone, and it's a recognition to everybody's effort that contributed to this program.
Fill us in a little bit on your journey. How did you get involved with coatings?
Well, so I think looking back, one of my areas of specialty really is in surface science, and this particular problem was started off as a technical discussion with another colleague, Greg Hatton, and I, where we were just thinking theoretically, what could we do to prevent these deposits from sticking to surfaces like this. So I reached into my background, which is both in surface science and in theoretical chemistry. So that part, at least on a theoretical level, then I would say transition to the more practical aspects of, okay, now we really have to deposit a coating. How do we do that? And so other people with that expertise, Dr. Ronghua Wei in particular, who's a specialist in coating technologies, particularly hard coatings and processes, became involved early on in the program. And we were also fortunate to have Dr. Kent Coulter, who is really an expert in large-scale manufacturing processes having to do with coatings. And so he was really key in scaling up the process and completing this transition to full commercialization, as well as the technical staff who put in long hours and also shift work. They were instrumental in being able to meet the production quotas that that were forced on us in order to be able to demonstrate or verify the performance of this coating technology in deep offshore wells.
So what do you enjoy about this field?
Well, I think the most enjoyable part of this whole project is to watch something go from literally simulations to benchtop laboratory work to pilot scale demonstration and then to full scale production. That's a very rewarding process to observe, I think.
From idea to reality, and it's making a difference.
Exactly, yes.
All right. Well, Michael, this is another example of a technology that I think is rarely in the spotlight, but yet it's so useful in getting us the oil and gas products we use every day. So a great peek behind the scenes today. Thank you so much for joining us.
Well, thank you.
And as I mentioned, SwRI picked up 2 R&D 100 awards in 2019. To hear about the award-winning AF369 direction finding antenna, check out last month's discussion, episode 16, Superior Signals Intelligence. And now, breakthroughs, personal stories of discovery told by the people who live them. Today, an engineer uses trial and error, data, and a lot of intuition to develop a cleaner engine.
Hi, my name is Brian Zavala, and I'm a research engineer here at Southwest Research Institute. So an after-treatment system is a system that's set up with different catalysts and also other injectors and other different devices in order to reduce the engine out emissions. And so you can kind of think about it as a system that sterilizes the exhaust coming out of the engine. So my story involves learning how to calibrate these systems. You know, we want to take into account the different operating strategies and regimes where these engines and after-treatment systems operate. And we also want to get the best performance out of these systems. And so we go through a calibration development phase where we define these parameters and where we sort of guide the behavior of the after treatment system. And so for me, doing it on these low NOx systems, being basically reducing the tailpipe NOx emissions to near zero levels, gave me a lot of exposure to really look at these systems in a different way. And so we have this iterative process of running these cycles, looking at the data, and then also going back to calibrating. And sometimes we have to do this on the fly, or basically while the engine is operating, if we see something that's that maybe a result that we don't want, or maybe if we see that there's an opportunity to make an improvement. And so, with that, again, going back to that intuition of being able to look at data for maybe 30 seconds, making the right parameter change, because there's got to be at least 120 different parameters you can change, and then knowing that you got the result that you wanted, that for me would be a breakthrough moment, because that tells me that I understood the system and that I made the correct assumptions about what was going on within the system. It's the goal of meeting this 0.02 regulation was really what the achievement was, and doing it on a system that was aged. So in other words, a system that is already at its full useful life, a system that you can no longer basically age or expose to deterioration mechanisms to. So this is a system that has reached its full service life, and those are the systems that are typically the most difficult to calibrate. That was a great feeling, because this is it's not only defining for, I guess, myself, but also for industry, because we could do it. So the part of the objective of the program is to say that the technologies that we selected are feasible to meet 0.02. And so, of course, if we don't meet 0.02, then the project didn't meet its objective. And so this would be kind of a pivoting moment, because we can say that, look, here's a set of technologies, and these are the ones we've selected. This is why we selected them, and they worked. So that kind of gave guidance to the regulators to say, okay, great, we can move forward with making new regulation. Ultimately, the goal is to clean the air, of course, for the environment, but also for human health, right? That's what the kind of the primary objective is of this program, and that's why California contracted us to do it. But yeah, for the end user in the next 5 to 10 years, the trucks that are going down the road are probably generating cleaner, the exhaust that's coming out is cleaner than what's actually going into the engine.
A breakthrough for better air quality. Thanks for sharing your story, Brian. And now, ask us anything. You ask, our experts answer. Today, a popular tech topic. Sammy M. asked, what is machine learning? Chris Menser is an SwRI engineer and assistant director in our Intelligent Systems division. He's here with an explanation. So, Chris, this is a term we should probably all become familiar with, machine learning.
Yeah, basically, machine learning has become really popular. What it is basically teaching a computer how to specifically do a task without explicitly telling it how to do that task. So typically for computer programs, you have a programmer and they know exactly what they want the computer to do. And so they type very specific logic that says, if you do this, then you do this, and things like that. But then that program isn't very flexible. So if it sees something it's never seen before, then it has a lot of trouble. And so that's where machine learning comes in. Instead, you have a programmer that creates a framework, and that framework is then you just put a bunch of data through that, and you tell it what you want the output to be based on the input. And that's how you teach the system, but you don't know exactly why it makes those decisions. And so this is a lot kind of based on how the human brain works. And so there's a lot of different methods that we can approach for this. But really it's, human brains, we see a lot of inputs with our eyes, ears, different senses. And all of a sudden, somebody tells us that's a car or that's a person. And so similarly, that's how machine learning is going to work. We've tried to mimic the human brain with neural networks, but there's also a lot of other more simple techniques. And so it's really great for scenarios where it's really hard to describe something very specifically and you want something that's very general, like all people look different, but you still want to recognize that they're people. Some examples of how machine learning is used. In particular, I work in the automated vehicle area, and so we do a lot of image processing. So we really want the vehicle to be able to respond like a human responds. And so if you see something, you need to know that it's a person. That's very critical to how you might drive. Similarly, you need to recognize that something is a car. And so those are all inputs that come in through a camera. Basically, they're just different colors and pixels. And how do you turn that into a concept? And so that's what machine learning is used for in automated driving. But that can also be used in really large data sets. People can use it in a lot of different areas, from your email, like trying to find junk email and things like that. And so it's really got a wide application.
Great explanation. Thank you, Chris, for being here today. To submit your question, use hashtag AskSWRI, comment on one of our Ask Us Anything posts, or visit podcast.swri.org and scroll to the bottom. Your question may be featured on an upcoming podcast episode. And that wraps up this episode of Technology Today. Subscribe to the Technology Today podcast to hear in-depth conversations with the people changing our world and beyond through science, engineering, research, and technology. Connect with Southwest Research Institute on Facebook, Instagram, Twitter, and LinkedIn. Check out the Technology Today magazine at technologytoday.swri.org. And now is a great time to become an SWRI problem solver. Visit our career page at swri.jobs. Ian McKinney and Brian Ortiz are the podcast audio engineers and editors. I am producer and host Lisa Benya. Thanks for listening.